In this question, we are given two particles of mass 3 and 5 kilograms. The one of 3 kilograms rests on a rough horizontal table, and the one of mass 5 kilograms hangs off the side of the table, 0.2 meters above the ground. The particle of mass 3 kilograms on the table is experiencing a constant friction of 12 newtons. The system is released from rest, and we have to answer these questions about the motion of the two particles. Okay, so let's see how we could do this. The first thing is to basically get a diagram. So I have my two particles, and I have a taut rope which is connecting them, and that's my pulley. And it's a smooth pulley, we're told, so we don't have to worry about friction forces on the pulley. And since the rope is taut and it's one rope, we're assuming that it's light and inextensible. We can ignore the weight of the rope, and we can say that the tension across the entire rope is actually the same. Of course, we need to define positive direction. So this particle is going to move to the right when the system is released from rest, so it makes sense to define right as positive. And also this particle is going to move down when the system is released from rest because this is heavier. So it's sensible to define downwards as positive as well. So now that we've got our diagram, let's consider the forces because we are going to have to do dynamics on this. So for the 3 kilogram particle, we've got the weight, obviously, which is just 3g because gravity is constant. And then because it's in contact with the table, we're going to have a reaction force, which is going to be completely opposite to the contact surface. So in other words, completely opposing gravity. So these two are going to cancel out essentially. But these two are not going to cancel out. And that's because the particle is going to move in the end. So this has to be bigger than this one. But this is obviously the tension from the rope. And the 12 newtons is the constant friction that the surface is creating in opposition to the motion. Okay, that's why this is going in the opposite direction to our tension. And lastly, the other particle, the story is much simpler here. It's only got two forces acting on it. Its weight, which is 5g newtons, and the tension, which is opposing the weight, obviously. Okay, so we're going to try and figure out for part A the tension in the rope and the initial acceleration of the entire system. Okay, so we want to apply Newton's second law. We want to apply it twice. We want to apply it once to particle of mass 3 kilograms, and then we want to apply it to particle of mass 5 kilograms. So when we apply it to particle of mass 3 kilograms, we're only really interested in horizontal forces because, like I said earlier, the vertical forces are going to cancel out. They're going to balance each other. And we can say that because the particle is not going to move up or down, right? It's only going to move horizontally, which means it's only the horizontal forces we've got to consider. So the force doing the leading is going to be the tension, and then the friction is going to oppose the motion. So the net force, which is going to make this thing move, is going to be tension take away friction, which is T minus 12, okay? And we know that that has to be equal to mass times acceleration. The mass is 3, the acceleration is what we're trying to work out, so we're going to call it A. So that's equation 1 for this system. And then we write down equation 2 by similar analysis, but now one particle of mass 5 kilograms. The weight of the particle, 5g, is going to make this particle want to move down, and the tension is going to hold it back, right? So the net force, which is going to make the particle move, is going to be 5g, take away t, and we know that the net force has to be equal to mass times acceleration. The mass of this particle is 5, and the acceleration is a, because the entire system is going to move with the same acceleration, okay? So now that we have two equations, what we want to do is we want to solve them simultaneously. And in this case, we have a t in one of them and a minus t in the other. So we just add them. And upon adding them, the t's are going to cancel. And the left-hand side is going to give me 5g minus 12. Okay. And the right-hand side is going to give me 3a plus 5a, which is 8a. And so there's only one unknown here, which is a. G is a number. So we rearrange this. We divide both sides by 8, and we get a to be 5g minus 12 over 8, which is 4.625, but we sort of write it to one decimal place or two significant figures. Turns out to be 4.6 meters per second squared, because obviously it's acceleration. Okay, so we've got A, we've done part of part A, and then we have to figure out the tension. Well, we can go to any one of these equations. And equation 1 seems nicer, doesn't have any g's in, so I'm going to go to equation 1, rearrange it to move that 12 to the right-hand side to get this. And now we know what A is, it's 4.6, but actually when you're doing these calculations, we only should be rounding right at the end. So when I put the A value into here, I shouldn't put in 4.6, right? The chances are you'll probably get away with it in most cases, but when you are doing this, it's good to get in the habit of actually putting in the formal answer, the proper thing that you've worked out to full accuracy, and then sort of working out the number to full accuracy, and then rounding. Okay, so in this case, once we've done the rounding, we get 26 newtons. So we've figured out tension and we've figured out our acceleration. Let's look at part B, which is the speed at which this particle, 5 kilograms, is going to hit the ground. So now we're going to start to do SUVAT, okay? Because we know that this entire system has an initial acceleration of 4.6, which is what we figured out. And we know that it's going to travel a distance of 0.2 meters. And both my acceleration is in the positive direction because the particle's moving downwards, and the displacement is in the positive direction because the particle's moving downwards, okay? And we know that initially the system is released from rest. So knowing three things, we can go to one of our SUVAT equations. In this case, v squared equals u squared plus 2as, and we can figure out what v is. U is going to be 0, so actually I'm just going to have 2as, and then I'm going to take the square root of that. But as I said earlier, we want to be putting in numbers to full accuracy. Okay, so when you do that, v turns out to be the square root of 1.85. Which is 1.36, and then the number carries on, but you round it, you get 1.4 meters per second to sort of one decimal place or two significant figures. Okay, so we answered part B. Now we're looking at part C, which is we need to figure out the distance traveled by a particle of mass 3 kilograms before it comes to rest. Okay, so two things are going to happen. So when the rope is taut, this particle is going to be subject to the initial acceleration that we worked out of 4.6, okay? But then when particle of mass 5 kilograms hits the ground, then the rope is going to go slack. So the particle, this particle of 3 kilograms is not going to have the acceleration that it had initially. In other words, this 4.6 is no longer valid, right? And we need to figure out a new acceleration. And we know that the acceleration, the new acceleration, has to be negative, because if it's not negative, then that tells us that this particle is going to carry on speeding up as it's going across. And we know that simply doesn't happen, right? What's going to happen is after the rope has gone slack, the particle is going to carry on moving, but then it's going to slow down more and more until it comes to rest, which means the acceleration has to be negative. And in that situation, you ask yourself, what is the thing that's actually causing the acceleration? Well, when the rope is slack, there's no tension, okay? But there is still motion because the particle had momentum, which means that there is still friction, because friction is only going to exist when there's motion. It's going to oppose the motion. So in other words, when this tension is gone in the second half of this particle's motion, or second phase of this particle's motion, the only force that's going to be having an impact horizontally, it's going to be the friction, right? So my new equation of motion, in other words, if I apply the second law again, because that 12 is in the negative direction, it's opposing my positive direction, I'm going to have negative 12, and that's the net force. And it's going to be mass, which is 3 times by the new acceleration, which is a new I'm calling, right? And I solve this to get the new acceleration for the second phase of motion, which is minus 4. And that minus is telling me that this is sensible, okay? So we have an acceleration for the second phase of motion. We know that when the second phase of motion starts is at the exact instance when this particle is going to hit the ground, okay? Which means that the speed of the overall system is going to be the same at that instant, which means the answer we worked out in part B, namely the speed at which the particle of 5 kilograms hits the ground, is actually going to come into play because that's the very speed that the particle of 3 kilograms is going to be traveling at that instant. Okay, so my initial velocity for the second phase of motion is actually going to be 1.4. And obviously, in the end, this particle is going to come to rest, so my final velocity has to be 0, right? And I again use v squared equals u squared plus 2as. In this case, my v is 0 and I want s, so I rearrange this to take my u squared to the other side, giving me minus u squared, and then I divide by 2a. So my s happens to be minus u squared over 2a. But again, when I stick the numbers in, I'm not going to stick in this rounded number. I'm actually going to stick in v equals the square root of 1.85. Obviously, in this case, the v of that being the u here, right? So when I stick that, I actually get my u squared being 1.85, and the minus on the outside is this minus here, and my 2a is going to give me 2 times negative 4, which is negative 8. And obviously when I work this out, I get a positive number. It works out to be 0.23125, okay? Now, this is the distance the particle travels in the second phase of the motion. This is not the total distance, right? The question, part C, says work out the distance traveled by the particle before coming to rest, which means So we have to add up both those distances, the distance traveled by the particle in the first phase, and then the distance traveled by the particle in the second phase. And we've only worked out here the distance traveled by the particle in the second phase, right? But we're in luck because we know what this height is, and we know that in the first phase, this string is taut. In other words, the distance traveled by 5 kilograms is got to be the exact distance traveled by 3 kilograms in the first phase of the motion, which means it has to be 0.2 meters, right? Which means the total distance traveled by my particle of 3 kilograms is actually 0.2 meters in the first phase and 0.23125 meters in the second phase, which is about 0.43 when I round it. Okay, so this is the total distance traveled by the particle. So we've answered part C. Let's think about part D, which is we've got to figure out the total force on the pulley. Well, if you think about the pulley, what's going to happen is we are going to have tension on the pulley acting this way and acting this way. Okay, this is from Newton's third law. Action has reaction. Okay, so this tension is going to be the same as this tension. And so we're only interested in the pulley. So we actually have a picture like this, which is we've got our pulley at the center and we've got our two tensions. And because of the way the table is set up, we know that this has to be 90 degrees. And we want to figure out the net force on the pulley, right? So if you think about what's happening here, we're going to have to figure out the sort of the formal vector sum of these two arrows, because these two arrows are vectors, okay? And these directions are really telling me my coordinate axes, or the positive directions of my coordinate axes. So this t is pointing backwards, which means, but the length of this arrow is t, the size is t, so this is going to give me minus ti. And likewise, the length of this arrow is going to be t, and it's pointing downwards, which is in the positive direction. So I'm just going to say this is going to contribute tj. And so I have my vector. This vector here is telling me the tension on the pulley entirely due to the ropes. And I want the magnitude of this vector because I want the total tension. I just take the magnitude of this vector, which is basically the component squared square rooted, right? And when I do that, negative t squared is the same thing as t squared, and t squared is obviously t squared. T squared plus t squared is 2t squared. But then I take the square root to 2 and the square root to t squared, which gives me root 2t. And we know what t is because we worked it out in part A. And again, I'm going to stick in this number to full accuracy. And when I do that, I get this number here, 36.59. So again, keeping to the accuracy we've been working with, the total tension on the pulley works out to be 37 newtons. Okay, so we've answered this question entirely. I hope this has been useful. If it has been useful, then do consider subscribing.